All right, so this is section 3.1 of Math 146. We're going to be talking about angles and their measures. For the most part, this is a review of stuff that was done in Math 145. We are going to add just a little bit extra in there. We're going to talk about um, arc length and the length of a circular sector. Other than that, it should pretty much be a review, but we are going to go through some things. So, a couple of things that we need to know about angles is that there are multiple ways to measure angles. Most angles can be measured either in degrees, that's horrible, degrees, or radians. All right, we'll talk a little bit really quickly about some of the pieces of an angle. First of all, an angle is going to be made by basically connecting two rays at a vertex. So an angle might look something like this. There you've got your two rays connected at a vertex, where this right here would be considered, in most cases, the initial side, where you start. And then this one over here is considered the terminal side, where the angle ends. And typically what you do is you put a little bit of a symbol in between, which shows that the angle started at the initial side and went to the terminal side. And a lot of times we label the angle, excuse me, with a Greek letter. A lot of times alpha, beta, gamma, theta, those are some of the most common ones. I prefer personally theta. It is probably one of the more common ones to use. So that's the way you're going to set up an angle. And if you're talking about something which is an angle made on a coordinate plane, basically like what would be an XY axis, the initial side is always going to be on the positive X axis of a plane. So for example, if this is your XY plane and I wanted to start an angle, the angle would start here and then it would rotate in whatever direction we're going to rotate, and then it would terminate someplace maybe right there. So that would be your angle. Again, starting on the positive x-axis and then finishing at its terminal side. Okay, so that's how basically angles are going to be made. So if we wanted to sketch an angle or two, we can do that real quick. Um, if I wanted to sketch an angle of what would be 45 degrees, once again, you would start on the positive x-axis, and hopefully we remember some things about how the whole degree thing works. 45 degrees is going to be basically be halfway between the x-axis and the y-axis in the first quadrant over here, and that would be a sketch like this of a 45-degree angle. Okay, pretty straightforward. One of the main things is that angles can be measured positively and negatively. A positive angle has a counterclockwise rotation. Counterclockwise rotation. Okay, and that's what you could see by what I just did. If I have a negative angle, like you would expect, it is a clockwise rotation. So we can do a real quick sketch of what a negative angle would look like. Let's say that I wanted to do, we'll just do a really simple one, a negative 90-degree angle. Once again, you would start on the positive x-axis, and then instead of going clockwise, you would go counterclockwise in this direction, 90 degrees, which of course creates a right angle, so that would be right there. So I'll make my arrow go a little bit further, and that would be a negative 90-degree angle. Or 1/4 of a rotation of an entire circle. So again, I am hoping that most of us remember that a full circle, a full rotation to get from the x-axis all the way back around to the x-axis would be 360 degrees. Just a real quick note, that there are ways to break the degrees down even further. You can break degrees down into minutes and seconds, basically just like you would think about a clock. As far as that's concerned, not exactly the same, but it's the same general idea. And you can put them into decimal forms as well. That is not something I am going to cover in this. It would be useful, I guess, if you're probably going into something where you have to deal with nautical issues like in the Navy and stuff like that. Not something I'm going to cover. It might be something that you could cover in some other kind of a class, but not really all that necessary. So I'm not doing minutes and seconds. We will focus strictly on degrees and excuse me, and then radians. So I did mention this thing called a radian, which again, hopefully this is a review. What I want to at least describe, however, is what a radian actually is. This may not be review. This just depends on who taught you the class in the last class and whether they covered this or not. I am hoping that they did. So here's your circle. What a radian is, it's actually a pretty easy concept if you think about it. A radian is something which measures along the arc of the circle, so it's the distance around the arc of the circle, the exact same distance of the radius. So let's say that the radius, because we know radius of a circle goes from its center out to the edge of the circle. Whatever distance this measures right here, for our example, we're just going to say that that's 1, but it doesn't have to be. Whatever distance that is, if I take that same distance, basically if you think about putting a string on top of the orange line there and starting it right here and laying that string along the arc of this thing, that distance would be 1 radian because it is exactly the same distance as the radius of the circle. So the radian would be that distance, 1 radian, would be that distance around the outside of the arc of the circle. So a radian is going to be 1 distance which is identical to the length of the radius measured along the outside of the circle. So then if I wanted to do 2 radians, then I would basically take that exact same measure of the radius and I would go ahead and put it over to here. However long that is, I might not be in exactly the same spot, but you get the idea because I'm eyeballing this. So that would be 2 radians. If I wanted to do a 3rd radian, you're getting the idea, hopefully I would measure it and it would come out to right about here. Okay, the reason that this is important, and again, I am hoping that this is review, is that you understand that half of a circle is measured to be pi radians. So 1/2 of a circle along the outside is pi radians. And if you look at what I just drew, it should make sense. I've got 1 radian, 2 radian, 3 radians. That little bit of a difference that we have between here and here, since we finished at 3, well, we're talking about pi here, that little bit in that green would be 0.14159, etc., etc. It would be the rest of the digits of pi. So basically all the way around would be 3.14159 so on radians. So that's how that works. And then a full circle is 2 radians. So 1 full revolution is 2 radians. Okay, again, I hope that that makes sense. So to find the actual length of the arc, if you're given one piece of information, or excuse me, if you're given some information, we can find it. I have yet to figure this out as far as why we call this S. I'm sure it has something to do with, its derivation in, Latin or some other language or whatever. But we call the arc length around the outside of the circle, or again, the length of if you measured and put a string at one point measured around the arc length, we denote that with an S. Again, that's the distance around the outside of the circle, kind of measuring the circumference, but not necessarily the whole thing. And S is defined to be the radius times the angle that is made. The theta, however, must be in radians. That is very important. Theta must be in radians. So for example, if I gave you the degree instead of the radian, you have to change it into the radian. Once again, that is something that should have been covered. I'm going to show you a slightly different way to convert radians and degrees than maybe you've seen before. It is really the same thing. I just think it makes it a little bit easier, because if you remember, there were two formulas. If you went one way, you would have to multiply it by pi over 180. If you went the other direction, you would have to multiply it by 180 over pi. And since it's the same thing, but the reciprocal, it's very easy to sometimes get those things confused. Well, I do it in a slightly different way so that you don't actually have to worry about it. The biggest thing that we need to know, and by the way, you're going to need to make sure you have that formula. That's important. The biggest thing we need to know for our conversion is that 180 degrees is the same thing as pi radians. If we know that, we can convert from radians to degrees or from degrees to radians very, very easily. Eventually, there are going to be some special values that you're going to need to know pretty quickly that will really help you for calculus. But for now, this is how you would do it. So what we know is that 180 degrees and pi radians are the same thing. So what I'm going to do is I'm going to set up a ratio of 180 over pi. Well, 180 is equivalent to a degree measure, so I would put a D on the top. And pi is equivalent to a radian measure, so I would put an R on the bottom. So it's just telling me that 180 is my degree, pi is my radian. Now, if I want to convert from degrees to radians, well, they're going to have to give you a degree. If that's the case, you're going to substitute it in for D, do a cross multiplication, and divide. If you want to convert from a radian to a degree, well, then you would plug whatever radian they give you in for the R in the denominator, cross multiply, and solve for D. So you don't have to memorize any specific formula. All you need to know is that 180 and pi are the same. So you set it up as a proportion here. Just keep it consistent. Technically, I could have written pi over 180. The only difference is now the R would be on top and the D would be on the bottom. It's going to work either way. So you can pick one of the two of these and go with it. So for example, let's do, this will actually be our first example. Let's convert from degrees to radians. We'll do two of these examples and then we'll go the other way. So let's convert 60 degrees into radians, and we'll convert, let's do a negative one. Let's do negative 45 degrees into radians. All right, so all we need is our little proportion here. So 180 over pi equals, since they gave me a degree, that goes where the D is, so that's going to be 60 over R, and now we can solve for our radian. And you might want to choose to use something other than R, since R tends to also represent the radius of a circle, which we may end up using. You can use a different variable if you would prefer. D is typically okay for degree. Again, this is just for your conversion. That's all that this is for. So let's cross multiply. We'll get 180R equals 60 pi. And then to solve for R, we simply divide both sides by 180. So R equals 60 pi divided by 180, and you will need to simplify 60 and 180. 60 goes into 180 3 times, so you should get pi over 3. Okay, this is actually one of the special ones that you're going to need to eventually know, that 60 degrees is pi thirds. We'll get into that a little bit later in the course. So 60 degrees is pi thirds. Okay, so now let's do negative 45. So once again, 180 over pi. The negative 45 is the degree, so that goes on top with the 180, and then r goes in the bottom for the radian. Cross multiply, 180r equals negative 45 pi. And then we'll divide by 180, so r will be negative 45 pi divided by 180. And 45 actually goes into 180 4 times, so that will give me negative pi over 4. So negative 45 degrees is the same thing as negative pi fourths in radians. All right, so now let's go the other way around. Example 2, convert from radians to degrees. And again, we'll just, excuse me, we'll just do a couple. So let's do pi over 6 radians. And again, I'll pick a negative one to do. Let's do negative 3 pi over 4 radians. Okay. The nice thing is it's exactly the same setup. You don't have to memorize any other formula. It's exactly the same thing. So we start off with the fact that we know 180 over pi. Okay, this time we're going 2 degrees and we're given the radian. So the radian goes in the bottom. So that's pi sixth. And d goes on top. We still cross multiply and divide. So we're going to have pi times d equals 180 times pi over 6. Okay, let's simplify that first before we do any more solving or dividing. So pi over d, 180 pi over 6 is going to end up, let's see, 180 divided by 6 is 30, so that's going to be 30 pi. And then simply to solve for d, you divide both sides by pi. So d is 30 degrees. So pi sixth radians is 30 degrees. That is another one you're going to need to know. I keep picking these because they're easy to deal with, but this is basically how it's done. Okay, let's do 3 pi over 4. So 180 over pi equals, in this case it's d over negative 3 pi over 4. Cross multiply, pi d equals 180 times negative 3 pi over 4. So if you have to do this without a calculator, certainly you can multiply the 180 on the top times the negative 3 pi and then divide it by 4. Personally, I like to do the division first if possible because I think making the number smaller is going to be easier before you multiply them. So 180 divided by 4 is going to be 45, but then we have to multiply that by negative 3. So negative 3 times 45 is negative 135. And don't forget the pi. And then over here we have pi d. So dividing both sides by pi, we get that d equals negative 135 degrees. So negative 3 pi over 4 radians is the same as negative 135 degrees. Okay, I did say we're only going to do 2 examples there, but I'm going to extend that to one more example where we want to convert 5 radians into degrees. The reason I'm bringing this up is because a lot of times people see 5 and they're like, but that's not a radian because it doesn't have a pi in it. It does not have to have a pi in it. If we go all the way back up to our little diagram here, notice that that's 1 radian. It doesn't have pi in it. That's 2 radians. It doesn't have pi in it. That's 3 radians. It doesn't have pi in it. A radian does not have to have pi in it. Most commonly, the more common ones do, but it does not have to have pi in it. So in this case, 5 radians would be, a good ways around the circle. Not quite all the way there because a full circle is 2 pi, which is, approximately 6.14. So that's not quite there to a full circle, but it's a pretty good ways around the circle. In any case, converting is still the same thing. So we're going to take 180 over pi. And in this case, we're still solving for the degree, so put d on top. 5 is the radian, so put 5 in the bottom. Cross multiply. Pi d equals 5 times 180. Let's see, 18 times 5 is going to be 90, so that's going to be 900. So to solve for d, you're going to divide both sides by pi, and you get 900 over pi is your degree measure. Okay, not really a descriptive thing, because that's not something that most of us can think of and conceptualize. What the heck is that number? And there's going to be a lot of times that you might be asked to do this in the calculator and give a decimal approximation for what this would be, which is perfectly fine if that's what it asks you to do. In most cases, I will probably ask you for this as opposed to a decimal, just because I want to make sure you know how to do it without just using a calculator to plug stuff in. But some of the homework assignments will require it, so you would just literally do 900 divided by pi. On your TI-84s, assuming that you're using that, and actually for most part, I think even like iPhone calculators and everything else has a pi button. So let's try not to use 3.14 as an approximation, because it really shortens it. So actually use the pi button when you have to do an approximation, because your decimal rounding might be off if you shorten pi to 3.14 as opposed to using what the calculator gives you for the actual pi button. So make sure you can find the pi button on your calculator and use that. All right, so that's converting back and forth between degrees and radians and degrees. So now what we're going to do is we're going to put this into applications. This might be something you haven't seen so far. We're going to use it to be able to find a couple of things. We're going to use it to be able to find the actual arc length, and we're going to use it to be able to find what is called the area of a sector, as well as different kinds of speed. So let's take a look at those. Extend the page here. So remember that our formula for arc length was S equals r theta, where S represents the arc length, r is the radius, and theta is the angle, but measured in radians. So really you could solve for any one of those three things as long as you have the other two pieces, right? I could solve for the radius if I knew what the arc length was and I knew what the angle was. I could solve for the radius. Or likewise, I could solve for the angle if I knew the arc length and the radius. I could solve for any of them. The way the formula is currently set up, obviously it's set up to solve for arc length easily. So let's just do that, and I think you guys are going to be able to manipulate the equation to do the rest of this. Let's say we want to find the arc length. So we'll call this, I guess, example 3, I think it is. So find the arc length if the radius is 10 meters and theta is 1/2 of a radian, or 0.5 radians. Again, that has no pi in it, but it doesn't matter. It's already in radians. We're good. So if I want to use the formula, it is literally just S equals R times theta. And that's it. So you're going to end up with 5, and you're talking about the length around the outside of the arc, meters. So that would be the arc length. If you had a circle with a radius of 10 meters and you wanted to go 1/2 of a radian around that circle, the arc length would be 5 meters. And then likewise, again, you could solve for theta if you're given other information. You could solve for r if you're given other information. I think this is pretty straightforward. This should not be a very difficult concept for you to do. All right, let's talk about the area of a sector. This is actually something that will be very important once you get to calculus 2, knowing this concept. So I know it's a little ways off before you actually get to it, but it's pretty important. So the area of a sector is given by the formula 1/2 r squared times theta. And once again, theta is in radians. So what does it mean by the area of a sector? So let me go ahead and draw my little circle over here again. And if I wanted to find the area of the sector, so there's the radius, and maybe I want to find the area of the sector right here. So I'm talking about this space. How much area does that thing have? Kind of looks like a triangle, but it's not, because one of the sides is curved. They're not all three linear sides. They're not all straight. So you have to use this idea of the area of a sector formula. Basically, if I know what the radius is, here's the radius, and I know what the actual arc is around the outside, what that thing is right here in radians, I can find what the area of that blue shaded region is. So that's how you find the area of a sector. So let's just say, we'll call this example 4, that I want to find the area where the radius is 2, we'll say 2 feet in this case, and theta is measured as 30 degrees. All right, so in order to find the sector, area of the sector, I need the radius. Well, they gave that to me, and I need theta. However, they gave me theta in degrees. We need it to be in radians. Okay, so this is where you would use your conversion. I'm not going to walk through the conversion here, but when you do the conversion, this ends up being pi over 6. I believe we actually did that one in our example up above. So we can now find the area of the sector, which is going to be 1/2 the radius squared times the angle pi over 6. So let's see, what is that going to give us? 2 squared is 4, half of 4 is 2, so we get 2 times pi over 6, which is 2 pi over 6, but that reduces to pi over 3. So this thing has an area of pi thirds. And again, that may not mean a lot of lots of certain people, but it's got an area of pi thirds. You could certainly plug that into a calculator to get a nice decimal approximation, which would probably mean a little bit more. I think it works out to be 1.05 or so if you go 2 decimal places. And it is area, so it should be a square unit, and it was in feet originally, so this should be feet squared. All right, I think that's probably good enough for the area of a sector. I don't believe that this next part is covered like in the homework assignments. The area of a sector may not have actually even been covered in the homework assignments, which again is okay, because I still think it's really important. But what you have, and I'm not going to go through a long, like a whole problem with this, I'm just going to try and describe what this is. You have 2 different kinds of speed associated with motion around a circle. You have what is called linear speed. That's one of them. Kind of an interesting one, because technically we're not on a line when we do this. It's going to be technically around the outside of the curve. But the linear speed is, if you kind of look at this drawing, it would be how fast something would be moving, let's go with red, around the outside of this. So if I started here and went to here, what is the speed that it would be doing around the outside of the arc? If you kind of think of it like being a circle track or something, how fast is that particle or person or car or whatever it is moving around the outside? That's what the linear speed is. So it's how fast something is moving around the outside. Well, the formula for that is v. Again, I don't know why they call that linear speed unless it means velocity, which I guess that would make sense, is going to be the arc length So the length around the outside divided by time. So now that I'm thinking about it, v for velocity makes perfect sense because it is a distance around the outside divided by time. Very much like miles, distance, per hour, time, miles per hour. So that's a linear speed. We also have something which is called the angular speed. Angular speed. And they actually denote that with, this is going to look very much like a W. I can't draw this very well. It's actually a Greek letter omega. I know it looks just like a W, especially when I draw it. And the formula for that is theta divided by time. So if you think about what that is, theta itself is the change, or how the angle is changing. So I'm going to go inside now and say that this part right here is your angle and how the angle is changing over that time. So that is what is called angular speed. And what I can tell you, and this is the best example that I can give, this is actually straight out of the book. It says that the angular speed is the way the turning rate of an engine is described. So if you think about what the engine in your car does, and you ever, looked at the dashboard and it says, something is going at 900 RPMs. That means that the engine is actually rotating at 900 revolutions per minute. So that is what is considered the angular speed. Linear speed and angular speed have a nice little relation, which I'm not going to go into right now once again. But those are, again, just two concepts that are really good to know. You probably didn't have to know them. Again, I don't think this is on the homework anywhere, and it's not something that I am actually going to cover on any kind of quizzes or anything, or tests, excuse me, or anything like that. So don't stress about linear and angular speed. But should you ever go into physics, and it's required to know some of this stuff, this will become pretty important. All right, I do believe that that is plenty enough for this video, just a one video lesson here. You should be good enough to go.